It again. Okay. So in this session, we're going to talk about working with geospatial data and knowledge graphs. You can find the slides dev.neo4j.com/NACIS2022 or that giant QR code. So a little bit about me. Like Amy said, my name is Will. I work for an open source database company called Neo4j. I'm also slowly working my way through the GIS program at the University of Montana. The best way to get a hold of me is probably on the Twitter there. Also a link to my blog as well. And I wanted to show a map that I created just to point out that I'm not a cartographer. That is as good as it gets in my abilities for cartographic design. I would love to talk about how I used one of those text-to-image artificial intelligence generators to help me get a dystopian Smokey the Bear. But instead, we're going to talk about data. And specifically, we're going to talk about thinking and working with data as a graph. So when I was thinking about how to relate graphs to cartography, I was thinking about the first time I heard about Tobler's first law of geography, which says that everything is related, but the things that are closer together are more related than the things further apart. And this made a lot of sense to me. So if we look at an example, so I live in Missoula, we're in Minneapolis right now, so cities like Bozeman, Coeur d'Alene, and Salmon, Idaho, those are closer to Missoula, so they're more similar to Missoula than Minneapolis. And this makes a lot of sense to me because this is a graph. So when we're talking about a graph, we're talking about a data structure. So nodes, these are the entities, relationships connect them. And we can have things like weights on our relationship. So Missoula is 1,002 miles from Minneapolis. That gives us some indication of the strength of that relationship. Missoula and Coeur d'Alene are a lot closer. That gives us some information about that relationship. So this is the graph that we're talking about. And a graph is, like I said, a data structure just on its own. This is kind of a mathematical concept. To make graphs useful, we need to be able to work with data as a graph. And this is where what's called the property graph data model comes in. So we can store arbitrary key value pair properties on nodes, on relationships to represent the data that we're working with. And this is why it's called a property graph. So another term you might hear is knowledge graph. And I like to think of a knowledge graph as really an instance of a property graph, maybe is a way to think of that. So where we have actual attributes, actual data that we're modeling as a graph. And in this case, we have some data about news articles. We know what topics the articles are about. We know what geographic regions those articles are mentioning. I think Google originally or at least has the most well-established, well-known sort of definition of a knowledge graph when they released the Google Knowledge Graph, talking about things, not strings, which is another really good way to think about this. So if we look at this example, we have an article about United States politics and China and Xi Jinping, and we have a canonical representation of the topic United States politics and government. That's not just a string attribute that we're storing somewhere. That's the canonical representation of that. So when we have multiple articles about this one topic, we can traverse that graph to find them. This, I think, is the real power of a knowledge graph. So we'll use this example to look at some example data that comes from the New York Times API. So I've been pulling in data from the New York Times API for, I don't know, maybe like a year or so. Every day they publish the most shared, most viewed articles. So I have a GitHub action that goes in and grabs that data from the API and loads that into a Neo4j database. So we'll use this as an example. Before we jump in, let's talk just a little bit about what is Neo4j and what is a graph database. So like other databases, like relational databases, use tables as the data model. Document databases use like a JSON document as the data model. Graph databases like Neo4j use a graph, so that data structure we were talking about, nodes are the entities, relationships, connect them. That's the basic data model that we're working with. We use a query language called Cypher to work with graph data in Neo4j. You can see an example in the upper right there. And Cypher is really neat because what we're doing is declaratively drawing sort of ASCII art representations of a graph. So what that query says is find addresses in New York that are connected to officer nodes by following this registered address relationship, and then find entities connected to these officers. This query comes from the Panama Papers data set. If anyone's familiar with that, this was a data journalism investigation by the ICIJ looking at offshore corporations and their connections to interesting companies and people. And this data of offshore corporations is very nested. There's lots of connections in it. It's like I own shares in a company that owns another company that's a nominee shareholder in a company that owns a boat. Do I own that boat? Yeah, you traverse the graph to find that. So ICIJ used Neo4j to represent this data and to try to find these connections. So it's a fun, and the data set's public, so it's a fun one to play around with. So because we're working with a graph, there's lots of interesting things we can do around graph analytics, data visualization, things like that. So there's really, I think, this spectrum of what we can call graph data access patterns, or maybe use cases is a way to think of it, from graph local, so local traversals where we're starting from a well-defined starting point. We want to maybe find the Minneapolis node in our news graph and traverse out from there, to the other end of the spectrum, which are these graph global operations, which we can think of as graph algorithms. So things like PageRank, find the most important nodes in the network, where I'm not interested in a well-defined starting point. I want to analyze the entirety of the graph. And there are things in between, but this is sort of a general way to think of the different ways that we interact with graph databases. So a little bit more about graph algorithms. So there are roughly three classes of graph algorithms. Things like pathfinding, these are really important in routing. So things like breadth first search, depth first search, or a star, where I'm taking into account weights on the relationships. Centrality algorithms like PageRank, find me the most important, the most influential nodes in the network. Or things like community detection or clustering, where I want to know what are the different clusters, what are the different groups in the network, and what's the strength of the composition of those clusters? How will they change over time? These sorts of things. There's other graph algorithms we can use for things like node similarity and machine learning workflows, but those three categories on the left, I think, are sort of the standard way that we think about graph algorithms. So, okay, let's take a look at our news graph data. So this is Neo4j browser. This is like a query workbench for Neo4j. And first off, here's our data model. So these the yellow node, these are articles. We have topics connected to the articles. We have organizations that are mentioned. Articles have photos, geographic regions, and people. Let's look for the most recent news articles and what geographic regions they are connected to. So if we look at this Cypher query that we wrote, we can see we're representing nodes. Let me make that a little bigger. Representing nodes in parentheses. And that colon article, this says find nodes with the label article. So label is a way that we can group nodes. You can think of it as kind of like a table from the relational database world. And then we're interested in sorting this result set by the published date in descending order. So find the most recent articles and then traverse out. So we draw this sort of ASCII art arrow that represents a relationship from the article to the geo nodes. And so these are the geographic regions that we're working with. And so if we take a look at this, we have, let's try to find some non-depressing news articles these days. Yeah, really. Here's some politics in Georgia. So we can traverse out by kind of clicking on these, and we can see, okay, here's the topics that these articles share. So we can traverse the graph that way to find what we're interested in. But we can also create more complex graph patterns in Cypher. So let's zoom out a little bit so it's a little readable. So maybe we want to know what news is relevant to me based on my location. And so this is actually find the georegions closest to Missoula, Montana, where I live, and then find articles and topics connected to those. So you can see we're able to just basically add on to this ASCII art pattern that we're drawing to find more complex patterns in the graph. And these graph algorithms, these are sort of built in to Cypher query language. So if we want to know what's the shortest path between two organizations, so in this case, what's the shortest path from the FAA to the National Park Service, we can do that by, again, just representing this sort of ASCII art representation. This asterisk here in the relationship, this is a variable length path operator. So this is saying follow as many relationships deep as you need to find where these nodes are connected. And they're connected through a topic, national parks, monuments, and sea, and a couple of articles, one about the National Park Service and one about the FAA. Cool, so let's go back to our slides here. These are just screenshots from the things we looked at. Okay, so that's fun, that's graphs, they're pretty, we can move them around, but what does this have to do with GIS and cartography? Let's take a look at some points, lines, and polygons. So let's jump over to QGIS. So here's QGIS, here's a lovely Robinson projection of the world, some natural earth shaded relief there. And I have the Python console open. So what I want to do is take a look at how we can use Cypher and Python to grab some data out of Neo4j and load it into QGIS to visualize this on the map. So we're going to first start off with just drawing some circles everywhere that we have some news articles that mention a region. We're going to plot that on the map. But we don't want to just draw the same size circle everywhere. We want to take advantage of this law of proportional ink. More important things should have more ink. They should be bigger on our page. I think that's one of Edward Tufte's principles. So I'm going to run this, and that grabbed some data, threw it on the map. Let's zoom in a little bit, and we can see that we have some nodes are bigger than others. If we look at the Python script, we're grabbing the Neo4j Python driver. We have a layer that we're creating in QGIS, and we want to use a graduated symbol renderer. So we've assigned 3 different renderers based on different ranges. We could do a bit more scientific approach to this, but this kind of works. And here's our Cypher query. So we're finding georegions connected to an article, and we're using degree centrality of our measure of importance. So that's points. Let's take a look at some lines next. So here what we've done is used article co-occurrence. So let's make this a lot bigger. There we go. So article co-occurrence, so by georegion. So what georegions are mentioned frequently in the same article together, lines connecting them should be bigger. And let's jump to polygons and just run this while we're here so that we can prove that we can. And then we'll talk about what these polygons are in a second. So we added some polygons. We've grabbed some protected places. So here, for example, this is Glacier National Park. Let's jump back to the slides and put that into context. We saw this, so we'll just skip through these. These are just slides in there for the reference. So these polygons, one of the things that graph databases are really good at are combining data sets and querying across them. And so I took one region from the USGS Protected Areas database and combined that with searching the ProPublica Congress API to find bills in Congress that have some legislation to do with given parcels. who sponsored those bills, what committee were they referred to, and so on. This was inspired by a project from Tony Canistra called Landwatch. His code is linked there. And so what we can do now, we can look at, this is another graph visualization tool. So if we look for maybe specific parcels, we can look at, let's find Glacier National Park. Glacier National Park, here we go. And we want to know, okay, what bills are connected to that, what legislators are connected to these bills, and so on. We can traverse the graph to find more information about these. So here's, for example, is a bill specific to Montana. We can see what committee it was referred to. We could traverse out from that committee and so on. So this is a visual tool for exploring the graph. We don't have to write Cypher. And really, the benefit of graph visualization alongside GIS tooling is it puts that data into context. So if I'm in QGIS and I click on Glacier National Park, I can open the attribute table and it can tell me, I know the area, I know the polygon this represents. But if I have the graph visualization alongside that, I have more information about what bills and legislators are connected to this parcel that I'm interested in. I'm working on a QGIS plugin for Neo4j, so rather than just Python scripts, we can have actually a nice plugin to bring in data. It's very early days, very initial development, but you can find some initial code, including those Python scripts that I showed on GitHub there. So I'll just leave you with a few resources to dig in more if you're interested. The online nodes conference, this is the Neo4j Online Developer Education Summit. This is coming up in a couple of weeks. I'm giving a much more technical version of this talk there, where I'm going to dive into how do I actually load this data into Neo4j, what are other tooling that I can use around this. So definitely check that out. There'll be a lot more also on other ways of working with geospatial data in graphs. If you're interested in just playing around with Neo4j, there's a free hosted version of Neo4j called Neo4j Aura, and there's some guides and data sets that walk you through that. The Panama Papers data set is one of the example data sets you can load and query in there. And then again, just the slides and a link to find me online. Thanks.
Great, thanks, Will. We can take one question.
Hi, thank you so much. I've been waiting for this talk for I don't know how many years, actually. So Neo4j and GIS and cartography. Tobler was all about how these different relations actually, in some sense, bend space and can be used to sort of understand, the different sorts of notions of distance and for us to analyze within that. So I'm just actually really curious, how does Neo4j at this point handle graphs that are densely connected, that are valued, and that may be pretty big? And you talked about these like global analysis algorithms, but then the examples you showed were kind of much more sort of localized. Can it handle really dense, big matrices that might represent migration or distances between things? Is it the tool for that at this point or not?
Yeah, so graph databases like Neo4j, so like building a database is a choice in choosing different optimizations and trade-offs, right? And so the choices and optimizations that a graph database makes is traversing the graph, and often this involves traversing very large graphs, right? So so the examples we showed, right, were more of those local graph traversals where we're starting from a well-defined starting point and traversing out. The benefit for working with large graphs that we have there is a property called index-free adjacency, which means that we can traverse the graph basically without taking into account the entire size of the graph. So I have basically constant time traversal for these local traversals. So that allows us to work with very large graphs in that sort of local traversal. On The other side, where we're talking about these graph global operations, things like PageRank, analytics, working with large graphs there. The way that we address that problem, so I say the graph algorithms that I mentioned, those are available as sort of a plugin for Neo4j. And the way that works is to basically build a projected graph into memory to then operate on these often iterative graph algorithms, like PageRank is very iterative. So there's oftentimes just a little piece of the graph that I need to project and load into memory. Like for example, when we were showing the shortest path between like the FAA and the National Park Service, if I wanted to run PageRank, I'm not interested in that whole path. What I'm interested in is that inferred relationship between those two organizations. So that's the piece that I would project into memory and then run PageRank on. So I guess the short answer to your question is for Graph Global, you still need to be able to project and load into memory on one machine that piece of the graph that you're interested in, but it oftentimes is not the same graph that's stored in the database in disk. It's often this inferred or projected graph, if that makes sense.